Good. Let's get started. Welcome to the first lecture of renewables and electricity markets. Today, we are going to talk about electricity market clearing from optimization versus equilibrium perspectives. So far in the last three lectures, we mostly covered electricity market clearing from optimization perspective, how we can formulate an optimization problem with objective function of maximizing social welfare if we have demands elastic to price, or if demands are inelastic, it reduces to minimizing system cost, generation cost. And then some constraints related to bids and offers, the capacity of generators, the consumption of demands, network constraints, and power balance equality. So it's a single optimization problem. But today we are going to talk about market clearing problem using a different tool, not optimization, but equilibrium. So just out of curiosity, how many of you knows about what equilibrium problem is mathematically? Anyone? Okay, so then there is something new also for you in this lecture to learn. So, like all previous lectures, before talking about the new content of this lecture, we are going to have a recap of what we learned in the previous lecture. So here I listed the outline of the previous lecture and different keywords from different parts of the lecture. It was a bit long lecture last time. So I suggested, like last time, we spent 5 minutes, you spent 5 minutes of reading these keywords, trying to remember what you learned, and maybe you can check it with your friend. Okay? So next 5 minutes to recap. Okay. Let's recap together. So the first item is fundamentals of day-ahead market clearing, gate closure. So in Nordex, based on Nord Pool, for example, do you remember when it's the gate closure for day-ahead auction? Yes? 12 noon of which day? A day before. So every day before D-1, we clear the market for every hour, of the next day. And today, the gate closure, based on the current practice, is noon of day D to clear the market for every hour of the next day D. Very good. Market time unit means the granularity, time intervals. Today, what is the time granularity of European day-ahead markets? 1 hour. Is it going to change? It is. In June 2025, it will be what? 50 minutes. Yes. And we discussed why, right? This provides more flexibility to flexible units like storage, others to participate in the market. Also, it helps renewables to have better forecasts, so they don't need to have one forecast, one bid for the whole hour. They can have different bids for every quarter. But computationally, the size of optimization problem for market clearing, is it going to increase? Is it? Yes, we are going to have 4 times more variables at least, right? Because now you are going to have a market price, market quantities, or production consumption quantities for every 15 minutes. So you can imagine the size of optimization problem will increase at least by a factor of 4. Very good. So we talked about at least two reasons why we have day-ahead market. Technical reasons and economic reasons. Can you remind me what those reasons are? Any of you? Please don't be shy. Yes?
Technical reasons could be the forecasting for renewables.
Yeah. The technical reasons? That's true. Okay, we need... No, the question is that why we need day-ahead market. Why not wait until real time, and based on the realizations of wind farms, I don't know, solar units, we can clear the market. Why do we need clear the market in advance, particularly here, a day before?
Also because some other generators they need some time,
Yes.
like a buffer before they can.
Exactly. Some conventional generators, I say conventional, like nuclear, coal, even gas, they need a buffer in time. They need time to schedule. They are not that fast. You have to tell them a day before at least how their schedule for production is for tomorrow. But if we change the market, the power system to be fully renewable, maybe that reason will disappear. Then we talked also about economic reason, not necessarily to have a market in day ahead, but any forward market, any market that we can clear in advance. It could be hour ahead, year ahead, day ahead, a week ahead, whatever. Do you remember what that reason is? Yes, please.
It reduces the power of producers.
What power?
If it's day ahead,
Yeah, you're right, but what power they reduce?
to sell energy at the price.
Market power. Market power. That's a term that if you are working in the market context, you are going to use it a lot. Market power means the power of people, especially in the generation side, to manipulate market outcomes for their own benefit. For example, they may bid at a price higher than their true operational cost, while knowing that still they will be accepted because the market needs them, right? For that capability, we say market power, and we showed that, not we, economists, they showed that more forward markets you have, less market powers the suppliers will pose. Now in European markets, there is something called remit, and it's a instruction, and it avoids everyone to play strategically, to bid offers not aligned with their true cost. So if someone does that, at least legally, it is forbidden. But the question is that how capable we are to recognize it, to identify it. Good. So then we discussed that in Europe today, we have a joint day-ahead market, a pan-European day-ahead market called STAC, right? Can you remind me what is the motivation of having a single market in Europe rather than one market in Denmark, one market in Sweden, one market in Germany? Why do we want to have one market? Anyone remembers that? I know most of you knows that. Just tell me. Yes.
I guess it's more efficient.
It's the matter of resource allocation, right? Remember one country at that moment, there is the lack of wind power, while in the other country, like Spain, they have a lot of solar power. So why not to let them to exchange power, right? So more resources you bring to a single union platform, more efficient you are in resource allocation. That's the whole point. It's not just power market. You can think of any market, right? And then we discussed about a joint algorithm under which we clear the day-ahead market in the European level. And it's called euphemia. So euphemia is not that different than what we discussed. Euphemia is just instructions or an algorithm. Do you remember what are the input data for euphemia? It's always hard to spell it, to write it. Euphemia, it's an optimization problem, right? What are the inputs to euphemia?
Transmission constraints.
Very good. Transmission constraints. Who provides this information to euphemia? TSOs, like Energinet. And do we have any other input? Yes.
Bids and offers.
Bids and offers. Bids of demands and offers of suppliers. Who provides that? NEMOs, nominated electricity market operators, like Nord Pool, like Apex. So at the end, we realized that Nord Pool is a bit offer collector, right? It's not the market clearing operator. It's the Euphemia joint NEMOs together under Euphemia algorithm. They clear stack. So what is the outcome? The market clearing outcomes, right? Productions, production quantities, consumption quantities, and most importantly, prices, zonal prices, right? And also the transfer between zones. So cross-border, I call it cross-border power transfers. So for example, how much we transfer from, I don't know, DK1 to Germany, or other way around. Very good. Network effect on market clearing outcomes. We may have different LMPs. Do you remember what LMP stands for? Locational marginal price. Do you remember why we may have different prices? In different geographic positions, we may have different prices? Yes? Congestion. If transmission line is congested, then we are going to have different prices. Congestion rent. Do you remember what that term means? Or congestion revenue. It's also referred to as congestion revenue. What's that? Yes? The grid owner, the earning of the TSO, or grid owner in general. So for example, we said that if we have bus 1 and bus 2, and the line is congested, let's say that the capacity of the line is 60 megawatt, and the power flow is 60 megawatt, it means that there is no more room for extra power to be transferred. Imagine that here the price is 50 euro per megawatt hour, while here the price is 40, sorry, opposite. 40 and here 50 euro per megawatt hour, right? So here the price is expensive, and this is the flow direction from bus 1 to bus 2. So how much the congestion rent will be for the TSO? Imagine TSO is like a spatial arbitrator. Buys power, 60 megawatt at this price, transfer it to bus 2, and sell it here at that price. So how much is the congestion rent? Yes? Yes. It's 60 megawatt times the price difference, 50 euro per megawatt hour, minus 40 euro per megawatt hour. So it's 600 euro. That's the congestion rate. Good. If the network is not congested, how much will be the congestion rate? 0, because the price will be the same. Good. So we discussed that, okay, TSO or grid owner in general acts like a special arbitrator, though in the market context they are regulated, they are not allowed to do that. So whatever they earn, they keep it in a pocket and they have to use it for grid expansion or grid operation purposes. So TSO cannot act as a profit maximizer because of the regulations. Otherwise, they are interested. Clear? Then we said that uniform pricing, considering congestion rent, is it budget balance or not? What we collect from demands, is it enough to what we pay to congestion rent for TSOs and to generators? Is it balanced? Yes. Uniform pricing is budget balance. Whatever we collect from demands, it's enough, and it is exactly equal to what we pay to generators and what we pay to the TSO in case of congestion. So then we formulate together market clearing optimization problem with extra constraint, grid constraints, right? Then instead of one power balance equality, we have one power balance equality either per node or per zone, depending our system is nodal or zonal. Good. Power balance equations. Do you remember we discussed that by Kirchhoff laws and Ohm laws, the way electrons, they flow from one point to another is based on AC, power flow equations. But we saw that, well, these equations are very nasty. They are nonlinear, non-convex. And if we put them in an optimization problem, that optimization problem becomes nonlinear, non-convex. What is bad? What is wrong with that? Yes?
It can be so hard to determine like the optimal you find is necessarily the global.
Very good. We will find a solution. That solution is feasible, no problem. But it's not guaranteed that that solution is globally optimal. It might be a local optimal point. We may find another solution, another point that provides us a better objective value for the objective function. Good. So that's why we use some very strong approximations, a lot of approximations we made together to end up to a linearized DC power flow equations. Now that equation is linear. So if you remember, we saw that based on DC equations, if this is bus N, if this is bus M, then the flow from bus N to bus M, F and M, is equal to susceptance of that line, its grid data, its input data, right, times voltage angle in N minus theta M, the difference of voltage angles. And as you see, this is a linear. B is parameter, thetas are variables. There is no nonlinear operator. There is no multiplication of variables, so it's linear. So it keeps market clearing problem linear convex. So if we solve the problem, we get a solution. That solution is for sure global optimum. Very good. Then we discussed about market clearing problem, nodal versus zonal. Nodal is the practice in US, zonal is the practice in Europe. So you are going to get prices in the nodal. We call them locational marginal prices or nodal prices. In Europe, we have zonal prices. So then we discussed that in European setup, there are different zones. For example, think of DK1, the whole Jutland as a bidding zone, and the entire Germany as one bidding zone. And then what we implement in Euphemia, we provide transmission constraints. Which constraints? The constraints between bidding zones. And do you remember what we call the capacity here that the TSOs they come up with? NTC, net transfer capacity. So TSOs in coordination together. Who provides that coordination? RCCs, regional coordination centers, like Nordic RCC in Copenhagen. They coordinate between TSOs to come up with this number, NTC. For example, they may say from this direction, 100 megawatt. In the opposite direction, it could be the same or different, 800 megawatt. Right? So this will be constraints for our Euphemia. Right? The TSOs, they come up with that. So if you think of that, it's like a constraint like this. So for example, from DK1 to Germany, and from, I don't know, the other way around, from Germany to DK1, for example, it could be something like this. This is the constraint you can have. So for example, from DK1 to Germany is 1,000 megawatt, while opposite is 800, for example. So any point within this box is a feasible point for you. Is it clear? Then we discussed that you are ignoring all the domestic line constraints inside the bidding zones. That's why you may need to have a huge redispatch to restore feasibility of the lines inside bidding zones. That's the problem. But on the other hand, you have only one price for the old zone. So one price for the entire Germany, one price for the entire DK1. Is it clear? Very good. Then we discussed that now Europe, for example, the TSOs in Central Western Europe, they started from 2015. Nordic TSOs started last November 2024, a new concept called flow-based coupling. Can you, one of you, explain me what flow-based constraints are? What do they add here? Do you remember? I might be a bit rushed last time explaining that. Do you want? Yes, please.
You include internal critical
Right.
lines.
Exactly. Imagine, for example, in Germany, we have some domestic lines, and imagine one of them is critical. Critical means that most of the times that line is congested historically. So we would like to reflect this constraint somehow in Euphemia while still having one price for Germany, not having two prices, not splitting it to two zones. We can do it to some extent. How we do that? By adding extra constraints that we call flow-based constraints based on something called PDDF, power transfer distribution factors, which are given data, input data to you. In Nord Pool, you can find those data. So what we say is that to Euphemia, then we add extra constraints. So extra input data to Euphemia are PTDFs, and also the remaining available capacity of critical constraints, RAM. So then we are going to have new constraints inside Euphemia saying that, for example, for a critical line inside Germany, for example, for line L, you'll say PTDF of, for example, zone 1 on critical line L1 times the net position of Z1. PTDF shows that if I increase the net position, for example, buying or selling the total, the position of Z1, how much the flow in line L1 will change, increase or decrease. It might be positive, it might be negative. It's a sensitivity. And you do it for all the zones you have. For example, PTDF, let's say that you have 10 zones, zone 10 on the line L1 times net position of Z10 less than or equal to remaining available margin of line L1, right? So somehow you are trying to impose a constraint about the constraint of the line L1, the critical domestic line, without splitting the zone. So still you are going to have one price per zone. So these constraints can be reflected like this. Now your feasible space is here, smaller than the previous feasible space. Is it clear? Good. I hope now you got, we had a clear recap of the previous lecture. Any question? Good. Let's now go to the new topic, equilibrium modeling. For me, this is a very fun topic, very interesting topic. It's at the interface of optimization and game theory. So if you like game theory, this could be an introduction to you. Okay? Let's for now exclude networks. We are going to add it later. Imagine you have two generators and two demands, both elastic to price. You can also add wind farm, but so far, for simplicity, we don't have just two conventional generators and two demands. So I think it's very trivial that production of G1, G2 will be 150. Consumptions of both demands will be 150. They will be fully supplied because their bid price is higher than offer price of generators. And the price, market price, is the price of the last generator dispatched, the marginal producer, which is G2 here, and the market price is 20. You agree? So imagine that, and already what we did, we developed this optimization problem, maximizing social welfare. Remember, the first two constraints are consumption limits. The second two constraints are generation limits. The last one is power balance equality. Dual variable gives you the market price. An objective function is the social welfare, utility of demands minus cost of generators. That's what we did before. So I have a question to you. Imagine you are the market operator and you release these results. Can you make sure that generators, demands, everyone are happy with your market clearing outcomes? The first question is that what does it mean they are happy? Is my question clear? You release this information as market clearing outcomes at 2 p.m. T-1, as they had market clearing outcomes. First question is that, do you mind whether everyone means market players, generators and demands, they are happy, they are satisfied with market clearing outcomes? First, do you mind? Second, what does it mean they are happy? Let's start with the first one. Do we mind they are happy?
I mean, everyone's offer and bid's been accepted in a way. So generator 2 met their demanded price, and the demand met their like they got their energy supply by less than their
That's true.
bid price.
But do you mind that maybe G2 calls you saying that you only accepted, how much, 50 megawatt of my, you only scheduled me 50 megawatt? I want it to be 60. Why you made me 50? Do you mind to receive that complaint?
Yeah,
You do. Why do we mind? Because people take complaint? We can tell them that we have an optimization problem. It works fantastically. We believe in that. I don't mind if you're complaining. We can say that. But shall we say that? Why not?
because we're still interested in them participating in the market
Yeah.
for like next.
Very good. Okay. We care about them. That's what we're saying. We like them to still keep bidding in the next hours, next days. I agree. Let me now go to the second question, and then we will back to the first question again. We like to make sure that they are happy. What does it mean they are happy?
I mean, I would maybe imagine they feel like they're
Fairly
fairly treated.
treated.
Yeah.
You know, in economics, fair is a very vague term. Fairness.
One trying to imagine is they feel like they're not being sort of like everybody else is getting like a better deal than they are.
Better deal.
Yeah.
Okay, better deal. If you get a better deal, how will it be reflected? In what measure?
Maybe you're paying less.
Profit. Profit. So when we are saying they are happy, what does it mean? Exactly. They got the profit that, they got the maximum profit they could. Can we reflect it better? If, okay, here there is no, the third generator, but imagine there is a third generator which is very expensive. We schedule that very expensive generator at 10 megawatt, and we schedule G2 10 less. In what? So now this is not optimal anymore, right? But in what measures it will be reflected? In profits of everyone, right? So now G2 will receive less, maybe demands will be unhappy saying that, look, I could pay less. Why you did that? Clear? So when we say people are happy, it means that we have a solution that they can't change it, not change it, they can't increase it by unilaterally changing their division, their strategy. For example, imagine we tell G2 you are going to produce 50 megawatt. If they realize that by producing less, for example, 40 megawatt, they are going to earn more, they will find a way to do that. Am I clear? So for example, we schedule G2 at 50 megawatt, and then the payment for them will be, the price is 20, the production is 50, so we are going to pay them 1,000 euro. If we schedule them 40, we are going to pay them 800. Hypothetically, assume that for some reasons, if they produce 40, their earning will not be 1,000, will be 1,010 or 1,200 euros. It means that what we offer them to do, it's not their best profit they could earn. Then they will deviate. Although we say that market clearing price is, outcome is for you is to schedule to produce 50 megawatt, they will find a way to deviate and go to 40 and earn more. Am I clear? So we have to make sure that everyone is happy. It means that no one can deviate from that outcomes to get a higher profit. Clear? Yes?
I just have a question regarding, are there any cases where the 20 euro price is only for producing 80 megawatts?
Yeah.
And like, if they only accept 50, for example, that they will actually, the price will be more expensive because they cannot, I don't know, maybe there are certain...
Yeah, you're talking about strategic bidding. Yes, which is not the part of this course, but yes, generators, they can bid. They can play with their offer price, which is 20 here. They can play with that, making sure that they manipulate the market price. Clear? But let's say that so far, for given offer prices, for given bid prices, we have to make sure that people, they wouldn't like to move from market outcomes. Yes?
Wouldn't it always only be the last generator on the line that could, because everyone
Yes,
else is
yes.
getting a higher price
Yes.
than it is. So it's always the last.
So when we talk about strategic bidding, which is not part of this course, it's usually the last generator, the marginal producer who wants to manipulate. Yes. Good. With this introduction, the question is that how can we ensure that everyone, G1, G2, D1, D2 in this case, are satisfied, and they don't have any incentive to deviate from the market clearing outcomes? So, for that, you mentioned, we want to make sure that they got their maximum profit that they could. This means that we need to develop their individual optimization problems. So, you as a generator or producer, you remember, what's your objective function of participating in the market? Maximizing profit. For demands, elastic demands, it's maximizing utility. And it was part of your assignment 1, task 1, how to calculate their profits and utility. Well, for generators, it's their production level times the price difference of market price and production cost. And for demands, it's the consumption level times bid price minus market price. Right? Good. So, if you are generator G1, what is, for example, imagine that they tell the generator G1, schedule, optimize your profit, and tell me how much we should schedule you. What will be the optimization problem of G1? Do you agree it will be something like this? That's the internal profit maximization problem of generator G1. Please look at it for a minute and tell me if you agree. Do you agree? So for G1, this is the optimization problem to be solved by G1. What is the objective function? Maximizing profit, which is its production, which is the variable, the only variable, decision variable of G1, how much I'm going to produce. That's the only things that the generator can change, times the market price. The market price, generator cannot change it. It's the market outcome, lambda, minus 12. 12, it's his offer price, which is assumed to be its true production cost. Subject to the capacity constraint. We can schedule that generator between 0 and 100, and 100 is the capacity. Do you agree? Good. So we can do the same for G2. Maximize profit. The variable is the production of G2, subject to internal constraints. What about this one? The utility maximization for demand D1. Do you agree with that? Do you? What is the objective function? Maximizing utility. The PD1 is how much D1 consumes. That's the decision variable, internal variable of demand D1, times 40. It's the bid price of the demand, the value of electricity for that demand, minus lambda, which is the market price. Subject to internal constraint, how much demand they have from 0 to 100. And the same for demand 2. So we have 4 participants. Therefore, we have 4 optimization problems. Do you agree? So the market price lambda is treated as a given parameter in each optimization problem. So these generators, they don't see how they can change price. They see market price as a given data. That's why we assume, okay, that's a word that I'm using here for the first time. These 4 participants, they are price taker. Price taker. It means that they take price as input data. They don't see how they can influence market price. They don't have any market power. Clear? So assuming these 4 agents are price taker, they don't see how they can manipulate price. They don't have any market power. They receive lambda as input data. Okay? Question. But we are going to clear the market. We need price. How do you think these 4 agents, players, they contribute to market price formation? Or let me ask another question. Recall the optimization problem for market clearing. Is there any constraint, any condition that we are missing? Yes? Power balance. We are missing power balance. Let's add that. This is power balance equality. So now we have 4 optimization problems and 1 power balance that says that total demand minus total production is equal to 0. Okay, the first 4 are optimization problems, but the last one is just a single constraint. There is no optimization there. Right? Let's do a bit mathematical fun thing. Can we reformulate? Remember, you learned about KKTs, right? Can we reformulate this power balance equality to be an optimization problem? Whose KKT is this? Can we do that? Let me help you. Do you think this optimization problem in the red box equivalent to the power balance equality? What is the red box? It's maximizing over lambda. Lambda times PD1 plus PD2 minus PG1 minus PG2. That's it, right? So it means that for this optimization problem, PD1, PD2, PG1, PG2 are input data because it's not listed under maximization. The only variable is lambda. So if you like to derive the KKTs, and there is no constraint, it's an unconstrained optimization problem. So if you like to find the optimal point, what do? You take derivative with respect to lambda. What is the derivative of this with respect to lambda? Just the term inside the parentheses. So PD1 plus PD2 minus PG1 minus PG2 equal to what when we derive KKTs? Equal to 0. That's the KKT conditions of this. So these two are equivalent. When you impose this optimization problem, implicitly you impose this condition. Right? They're equivalent. Good. By saying that, they are equivalent because if you derive KKTs, it's that one. Then let's remove this power balance equality, and instead of that, we impose this optimization problem. Why we do that? Now because we have 5 optimization problems, not 4 optimization plus a joint constraint. We don't like it. Let's make it 5 optimization problems. Okay, but for the other 4, we know who are solving that, G1, G2, D1, D2. But who is solving the red box, the red optimization? Let's assume there is a fictitious player. Let's call it price setter. Price setter. Why we call it? Because the only variable of the red box is lambda. It's price. So let's call it price setter. And price setter, it comes by the name, it sets the price. Okay, now we have this 5 optimization problems. Hope you agree with me. Okay, now I'm trying to introduce you to game theory. An equilibrium problem. A question. Can we solve these 5 optimization problems separately? Can we? Can I solve problem for G1 separately than other 4? Yes? No. Why? They are interdependent or interrelated. So why what does make G1, oh, sorry, what is the reason that G1 is interconnected to others? Lambda. Who is determining lambda? Price setter. So G1, G2, D1, D2 are connected to price setter. So can I solve the price setter problem first, designate price, and then we can solve the others independently? Can I do that? No. Can I solve the price setter problem independently than others? Look at the price setter problem. No. We like to solve everything in one shot, not iteratively, in one shot. So to be able to solve the price setter problem, what do I need? PD1, PD2, PG1, PG2. And also they are coming from 4 other optimization problems. Do you see what I'm saying? So apparently I'm writing more than before. So we have G1 optimization problem, G2 optimization problem, D1 problem, D2 problem, and you have price setter optimization problem. Let me use different colors. So G1 provides PG1 to price setter. G2 provides PG2 to price setter problem. D1, this optimization provides PD1. And this one provides PD2 to the optimization problem. and in other way around, then it provides lambda to the optimization problems. Do you agree? As you see, these 5 optimization problems are interconnected. We can't solve each of them separately. Yeah, you can solve it iteratively, but let's say we want to solve it in one shot. Is it clear? Good. So the answer to the question in this slide is no. And why we discussed, right? Good. The reason is that the market price is a variable in G1, G2, D1, D2 problems. It's a parameter there while it's a variable for price setter. On the other hand, production and consumption levels are variables for G1, G2, D1, D2, while they are parameters for price setter. So it means that, do you agree with that? All these 5 optimization problems are interconnected and should be solved together. We can't solve them separately. So when you have multiple optimization problems to be solved together, you have a game theoretic problem. This is an equilibrium problem. Equilibrium problem is equilibrium problem includes multiple dependent optimization problems. Is it clear? If you have 2 or more optimization problems that they are interconnected to each other, it's an equilibrium problem. It's a game theoretic problem. Clear? By the way, in game theory, we have 2 main fields of cooperative game and non-cooperative game. Do you think this is cooperative game or non-cooperative? Let me explain you. In non-cooperative game, everyone tries to maximize its own objective function. In cooperative, what we do, we say that we are all in the same boat. Let's solve a single optimization problem. All together, we earn $1,000. Now, ex post, let's think how to distribute $1,000 among us. So this is cooperative or non-cooperative? This is non-cooperative. Everyone is selfish. Everyone tries to maximize its own profit. Clear? Okay, let me continue by 5 minutes, and then we have a break in 5 minutes, okay? This is very important. Please pay attention. Do the players, we have 5 players here, 5 optimization problems. Players are G1, G2, D1, D2, price setter, 5 players. Do the players influence each other's objective function? Yes? Yes. You see lambda in G1, G2, D1, D2's objective function. You see PG1, PG2, PD1, PD2 in the objective function of price setter. So the answer is yes. The next question. Do they also affect each other's feasible space? Feasible space means constraints. Do they? No. The constraints of everyone, G1, G2, D1, D2, it only depends on the internal variables. And price setter has no constraint. So the answer to the second question is no. We like that. Because this is an equilibrium, but what class of equilibrium? Nash equilibrium. The Nash equilibrium is an equilibrium that different optimizations are interconnected, but only in the objective functions. It means that if, for example, me and you, we have equilibrium problem, my strategy affects your objective function, your decision affects my objective function, but we are not impacting our feasible space. It's called Nash equilibrium. It's an easier problem. You can take a game theory course and see that Under Nash equilibrium, we can explore existence of the solution and uniqueness of the solution. We like it. What we don't like, and it's not the case here, is that variables also impact the others' constraints. Then it becomes something called generalized Nash equilibrium, in abbreviation GNE. And then it's hard, in general, to explore properties of the game, including solution existence and solution uniqueness. Unless for a very specific type of GNEs, exploring those properties is impossible. Am I clear? Good. So we learned this is NE, not GNE. It's a Nash equilibrium, not generalized Nash equilibrium. This specific problem, equilibrium problem, is also referred to as competitive equilibrium. Competitive equilibrium. Everyone tries to maximize profit, and price setter tries to set the price. This competitive equilibrium is a very well-known problem. There are at least three seminal works, very important, influential papers that come up with this competitive equilibrium. So what we discussed here, it ended up in 4 Nobel Prizes in economics. It may look easy, but there is a long history there. So the first one is a paper by Leonid Kantorovich, who got Nobel Prize in 1975. He is the kind of founder of linear programming. And in 1939, he wrote this paper, Mathematical Methods of Organizing and Planning Production. That time, he didn't call it competitive equilibrium. He called what? Planning production. But the paper got accepted for some historical reasons in 1960. As I said, this person is recognized as the founder of linear programming. Then this paper, Spatial Price Equilibrium and Linear Programming. If you read that paper, it's amazing. And now after my explanations, you can read the paper and understand. He's the one that called price setter. To my best knowledge, he's the first one called price setter for the fictitious player. So also Paul Samuelson, he got Nobel Prize in 1970. Then there's another fantastic paper by Kenneth Arrow and Gerald Debrew. Existence of game solution, right? Existence of an equilibrium for a competitive economy. Now they call about equilibrium, competitive equilibrium. And both gentlemen, there is a typo there. It's not Paul Samuelson. It's Kenneth Arrow and Gerald Debrew. Both of them, they got Nobel Prize in 1972 for Kenneth and for Gerald Debrew in 1983. So you see that how rigorous foundation there is for this problem. Good. If you want to learn more about game theory and for market applications, including energy market applications, this book is amazing by my colleagues Stephen Gabriel, Antonio Conejo, David Fuller, Ben Hobbs, and Carlos Ruiz. And Steve Gabriel every year runs a master/PhD course at NTNU. It's a short course for 5 days, so it's easy to handle. So if you wish, you can go and take that course. Usually my PhD students, they go and take it. He has 2 courses, the basic course, I think this is the basic course, and 1 more advanced course. Okay, I think it's good to stop it here and then take a 15 minutes break. And remember, there will be another Kahoot at the end of next lecture. Okay, let's move on. Any questions so far? There's a very nice question in the chat box. So Paul asked that, okay, you mentioned about Nash equilibrium, NE, and generalized Nash equilibrium, GNE. So GNE is in the case if we impact each other's not only objective function, but also constraints. While Nash equilibrium, it's an equilibrium that only objective functions are interacting. So constraints are not dependent of others' strategies. So he asked if we consider grid constraints, does the problem become a GNE? The answer is no. Why? I'll explain it in one of the upcoming slides. So even by adding network constraint, the equilibrium problem remains NE, not GNE. Why? The answer is coming in maybe half an hour. That's one thing that I wanted to tell you. The other one, we talked about this kind of structure, right? How these five agents, players, they are interconnected. And we said we like to solve it in one shot. That's why we can't solve them separately. I'm not going to talk about this in this course, but there is an approach that you can solve this kind of game iteratively in multiple runs and find the solution. Can you tell me what kind of iterative approach we can use here? Any idea? Yes. No. I thought there's a. Yes, please. Yes. Very good. Very good. Yes, exact. For example, you can start with initial lambda, some initial guess. Say price is $10 per megawatt hour. Send it to G1, G2, D1, D2. See how much they produce or consume. And then as a price setter, you can see whether the power balance equalities hold. If not, you can use some gradient methods to now update lambda as a function of how much imbalance you see. And iteration number 2, send new prices. So it's called something as Walrasian auction. Walrasian auction, which is exactly this iterative algorithm. So if I remember correctly, Walras was a French economist long time ago who proposed that. And if you do that, it's called in French tâtonnement process. I don't know if you have a French here. I heard it means blindly looking for. Is it correct? No French here? Okay, good. Let's continue. At least my colleague Pierpenson told me it meant, so I had a French confirm that. Let's move on. Now, another economist I show you, he also got Nobel Prize, John Nash. Beautiful Mind movie, right? Maybe you watched. His main contribution, or one of his contributions, is that he come up with something called Nash equilibrium point, the definition of Nash equilibrium point, and he proved the existence of that kind of solution. What does it mean? So he said if a solution to our equilibrium problem exists, there will be a Nash equilibrium point. So we formulated together a Nash equilibrium game. And he says if a solution for that exists, under that solution, no market participant can increase its profit, or in general the objective function, by deviating unilaterally, it means that alone, from the equilibrium solution. So what it means, so if based on the market clearing outcomes, for example, if we say that G1, you are going to produce 100 megawatt, and the price is 20 euro per megawatt hour, and therefore your your income is what? 2,000 euros. And for G2, I don't know, whatever it is, for example, 1,000 euros. So under Nash equilibrium point, there is no way for G1, G2, also for D1, D2, to change their strategy, for example, to move 100 megawatt to 90, and by that to get higher profit. Is it clear what I'm saying? So Nash equilibrium is a point that everyone is happy to stay there. If they change their decision, they will not earn more. Either they will get the same profit or they will get less profit. Clear? So that's the definition of Nash equilibrium point. So recall, what was our original question we started this lecture? How can we ensure that everyone, G1, G2, D1, D2, they are happy with the market outcomes, and they don't have any incentive to deviate from it. So if we show that the market clearing solution is a Nash equilibrium solution, then we answered that. No one will deviate. Are you following me? Good. Now I would like to add more questions to you, impose more questions. In the last lectures, you learned about optimization problem, how we can clear a market using an optimization problem. Today, I taught you how you can formulate an equilibrium problem. And both of them can be used for market clearing. So my question to you is that which one we should use if you are the market operator, if you are the one that's running Euphemia, if you are the CAISO, California ISO, which method you are going to use to clear the market? Are you going to solve an optimization problem with maximizing social welfare, constrained by production limits, consumption limits, grid limits, power balance equality? Are you going to use that method? Or are you going to formulate an equilibrium problem, a profit maximization problem for everyone, and a price setter, and you are going to solve that one? Which one are you going to use to clear the market? Do you have any answer for now? Yes?
Whichever one's faster.
What, pardon me?
Whichever one is faster.
Which one is faster? Okay, let's not talk about faster. Let's say that you have supercomputers. You can solve either of them quickly. Which one you are going to pick? Are you going to try to solve a single optimization to maximize social welfare, or you're going to solve equilibrium problem to make sure that everyone is happy? Is my question clear? And if you say equilibrium, how are you going to solve that? It's 5 optimization problems. You like to solve them together. Here in our example, it's 5. Maybe in reality, it's 5 million. How are you going to solve that? Any method? Of course, we discussed iteratively, but let's say we like to solve it in one shot. So that's what we like to now talk about. So, optimization problem, what we learned from previous lectures, maximize social welfare subject to production limits, consumption limits, power balance. If you have network, also grid constraints. The second alternative is equilibrium. Every generator or every producer tries to maximize profit subject to production limits. Every demand tries to maximize utility subject to consumption limits. And also we have a single unconstrained optimization for price setter. So here I'm not talking about grid yet. Grid network, we are going to talk about that later in a few slides. So you have 2 options to solve, not to solve, to clear market as a market operator. Which one? A debate here. Who says optimization? Almost 20 people. Who says equilibrium? Almost 10, 15. Who says none? Or he says both. Let's try to solve both and see what happens. You say both? Yeah, it's fun to solve both. But the problem is that euphemia should be solved in 16 minutes. We like to increase granularity to 15 minutes. Harder problem now, you would like us to solve 2 problems, optimization, equilibrium. And if they give us different solutions, what to do? Which one to pick? Good. Let's stick to equilibrium for now. Also, there's no answer in online, in chat box. Equilibrium, how can we solve it? We have 5 optimization problems, remember, right? G1, G2, D1, D2 price setter. How can we solve it? You learned some powerful mathematical tool, which is what? KKTs. KKTs are your friends. You are going to use it everywhere. Do you have any idea how we can solve this problem by KKTs? Replace every optimization problem by its corresponding KKT conditions. Optimization for generator, replace it by KKTs. Optimization problem for demands, replace it by KKTs. Optimization for price setter, replace it by KKTs. You remember, KKTs, there is no objective function in KKTs, right? It's just a system of equations. Some equalities, some inequalities. So if you collect many KKTs together, coming from different optimization problems, it's still a system of equations, right? So what I'm saying is, you have optimization 1. If it's convex, derive KKTs, then KKTs are necessary and sufficient conditions for optimality. You have optimization problem 2, and we know that they are interconnected. Derive KKTs. If the optimization problems are interconnected, also they are interconnected. System of equations, system of equations. Put them together. Put them together. A bigger system of equations. And we call this problem mixed complementarity program, MCP. System of equations coming from 2 optimizations. Here you have more optimizations, no problem. Replace each optimization by its corresponding KKTs. And as I said, now it's a system of equations, including complementary constraints. That's why we call it a system of equations which is mixed complementarity problem, MCP. And there are solvers like path that you can solve any MCP using that solver. Good. Let's get back again. Now we know how we can solve equilibrium. Now, original question we had, which problem to pick to clear the market? Still, you don't have any clear idea which one to pick? Okay. We saw that from equilibrium we can derive MCP. The other one, optimization, it's a single optimization problem, maximizing social welfare. Also for that you can derive KKTs. For any optimization problem, you can derive KKTs. This is important. We can compare KKTs coming from optimization to the MCP, which is the collection of KKTs of different optimizations in the equilibrium. If MCP of the equilibrium and KKTs of the optimization, if they are identical, then optimization and equilibrium, they are equivalent. What I'm saying is, if you have an equilibrium problem, if you have an optimization problem, drive KKTs, put them all together, which is MCP. If they are equivalent, then optimization and equilibrium, they are equivalent. So if KKTs of two things are identical, those two things are equivalent. Clear? Now, do you see where I'm going for? This is your optimization problem, equilibrium problem, right? G1, G2, D1, D2, and price setter, the original optimization problem. Are you ready to derive KKTs? Let's do that. For example, the first one is optimization of G1. So your internal variable is production at G1. You are trying to maximize your profit, which is PG1 times lambda minus 12. 12 is your production cost. Lambda is the market price. Subject to PG1 is between 0 and 100. And dual variables are mu underline G1 and mu bar G1. Remember the first things we do? We write it in a standard form. So we make it first minimization over the same variable. You multiply the objective function to a minus. So it becomes PG1 12 minus lambda. You multiply to a minus. It's now minimization. The constraint should be in a form of lower than or equal to. So PG1 minus 100 is less than or equal to 0. The corresponding dual variable is mu bar G1. The other constraint is minus PG1 is less than or equal to 0. The corresponding dual variable is mu underline G1. Right? Now you can derive the Lagrangian function. Let me use a different color. So the Lagrangian function is a function of primal variable and dual variables, which is equal to the objective function, PG1, 12 minus lambda, plus mu bar times the left-hand side, plus mu bar G1 times PG1 minus 100, plus mu underline times, again to the left-hand side, so you have a minus here, minus mu underline G1 PG1. Right? Now you can derive KKTs. The first thing is that the derivative of the Lagrangian function with respect to the only primal variable you have, which is PG1. You have PG1 here, here, and here. So it becomes 12 minus lambda plus mu bar G1 minus mu underline G1 equal to 0. Clear? You don't have any equality constraint, but you have two inequalities, so then you have two complementarity conditions. So for this is PG1 minus 100. It's less than or equal to 0. Mu bar G1, it's non-negative. And the product of mu bar to PG1 minus 100 is 0. It's a complementary constraint. And then for the other one, mu underline G1, we can write exactly like this. And PG1, this is P, this is mu, underline G1, non-negative. That's the KKT conditions you have. That's the only three. So by that, you can derive KKT for every single optimization problem. You see, it's exactly the same. You can do for every single. So now, not now. Good. You can put all KKTs together, and this is MCP, Mixed Complementarity Program. Now let's do one thing else. Remember, this is your optimization problem. Optimization problem for market clearing, that's what you learned in lecture number 1. You maximize social welfare, the bid price based on the bid price of demands minus the offer price of generators, demand constraints, generation constraints, and power balance equality. That's what you did. You will learn in lecture 1, and also now you are doing it for task 1 of your assignment. If at home you derive KKTs of this optimization problem, it's exactly the same as this. So what do we learn? We learned that the optimization problem, social welfare maximization, and equilibrium problem under which we maximize profit for everyone, they are identical. So what do we learn? We learned that while not about computational, which one is easier to solve? Do you prefer to solve single optimization, ask Julia Python to solve it? Or do you prefer to write 5 optimization problem, maybe 5 million optimization problem, depending how many players you have, drive KKTs, put KKTs together, ask PAS to solve? Which one is easier? Single optimization problem. So yes, when we clear the market, we maximize social welfare. But the solution for that optimization problem is also a solution to an equilibrium problem. And since it's a solution to an equilibrium problem, it's a Nash equilibrium problem, so no one will deviate. So it means that when we clear the market by maximizing social welfare, implicitly, we solve equilibrium problem, and everyone got the max profit they could. So at the same time that we maximize social welfare, at the same time everyone is happy. It's a perfect market. We call it perfect competition. We maximize social welfare, everyone is happy. So now you get why we all talked about the equilibrium problem, right? So the takeaway is that, sorry, the takeaway is that equilibrium and optimization forms of market clearing problems are equivalent because their corresponding KKT conditions are identical. And second, both forms lead to Nash equilibrium solution, meaning that no market player has the incentive to deviate from the market clearing outcome. If G1 received 2,000 euros, it's the best it could earn. Clear? So, a question. If for any reason, that reason could be any externality. Externality is also economic terms. For example, tariffs. For example, market power. For any reason, if we ruin this equivalency, if our market clearing problem with maximizing social welfare, if hypothetically it doesn't anymore have any equivalent equilibrium. So do you think then players may have incentive to deviate? Is my question clear? Here I said that our equilibrium problem and optimization problem are equivalent because KKTs are equivalent. But imagine hypothetically, now we have an optimization problem for market clearing which doesn't have anymore an equivalent equilibrium. Then can we say that our market clearing solution based on optimization is still a Nash equilibrium? Not anymore. Can we say necessarily no one will deviate? We can't say anymore. And I showed you this equivalence between equilibrium and optimization based on perfect competition. But there are some reasons that I'm not going to talk in this course, but like it could be part of tariffs, it could be any out of the market payments, any side payments, it could be any market power, any different reasons that may ruin this equivalence. And if that happens, then the market clearing outcome based on social welfare maximization might not be equilibrium point anymore. So the answer for this is no. Is it clear? Good. So this is what you learned in lecture number 3. Market clearing as an optimization problem now with grid constraints, with nodal grid constraints using DC linearized equations. Do you remember that? The simplified version of this is the zonal one, but I picked this because this is more constrained. This is the nodal market clearing with grid constraints representing a network in a nodal way, not zonal. Power flow equations are represented using linearized DC power flow. You remember that, right? We discussed that last lecture, and you are going to solve task 3 of your assignment based on that. This is form 1. Form 2 is this, writing it as an equilibrium problem. Why I'm saying it's equivalent? Because you can derive KKTs of form 1, form 2. You can explore that the KKTs are identical. So please check this equilibrium model in a more general way. There is not one generator or two generators anymore. There are for each generator, for each demand, for price setter at the bottom. Now also we have one extra box. Please check it what it is for a minute. Maybe you can check it with your friend. What is the middle box? Anyone would like to say a few things? What do you see here? Yes? Very good. So let's start with the first box. It's generator. Can you tell us what is that? Still, it's profit maximization, right? Very good. So we say for every generator or every producer G, maximize profit, we wrote lambda n, where len n hosts generator G. So now we are talking about not every lambda, but the lambda, the nodal price that generator G is located there, minus the cost. So that the first box is the box of generator, profit maximization for the generator. Profit of producer G, constraint G, internal constraint for producer G. The same goes for demand. Still, we are maximizing the utility, means the consumption of demand D times the bit price minus the price. Which price? The price at bus N, at bus N, that host that where demand is located there, subject to demand constraints. Since now we have buses, nodal setup, now the price setter, the variable of the price setter is not just one lambda, there is one lambda per node, lambda n. That's why we have sum over n. Still, it's a single optimization problem. One problem for the price setter, although you have different nodes. So now this is power balance for each node. And again, if you take a KKT with respect to lambda n, you are going to have one power balance per node. Very good. So far, it's the same as what you saw. But now you have a new box. We have a new box, which is this one. That box belongs to grid owner. Remember, what's the objective of the grid owner if it's not regularized? Yes? Maximize congestion rent. Okay, so we are going to back to objective function. Can you tell me that what these constraints are? The power flow constraints, yes? So it says that the power flow at any line connecting buses N and M is restricted by capacity and minus capacity. Minus capacity to consider the opposite direction. Good. So the objective function, it is congestion rent. Why? For example, imagine the two buses, let's say bus 1, and this is bus 2. This is lambda 1, this is lambda 2. The price in bus 1, price in bus 2. Remember the flow, the power flow from 1 to 2 is B, the susceptance of that line, theta 1 minus theta 2. That's the flow, right, based on linearized DC power flow. So if you check that one, the objective function, so it says lambda 1, lambda n. Let's say n equal to 1. Lambda 1, B, theta m minus theta 2. It's theta 2 minus theta 1. That's when n is 1. Now if n is 2 is plus lambda 2, the same B, theta 1 minus theta 2. Right? Which is the same as B, theta 1 minus theta 2, lambda 2 minus lambda 1. This is the flow. What it says is that you sell the flow at price lambda 2, that's your revenue, minus the flow times lambda 1, what you bought here. It's the congestion rate. Is it clear? So let me back to the question online and also the question I shared with you. The question is that, does adding constraint change equilibrium problem to not be NE? It make it GNE. Let me ask. Let me formulate the question better. Now we have 4 types of optimization problems. Do you see any way that they are impacting each other's constraints? Are they changing constraints of each other? No. For generator, constraints are only based on internal decision, PG. Only lambda, which is the price setter's variable, impacts that. The same for demand. For transmission owner, lambda, which is the price setter's decision, impacts the objective function. But the constraints are only dependent on theta, which is the internal variable of the transmission owner or transmission system operator. Price setter, there is no constraint there at all. So this is still Nash equilibrium. It's not GNE. So adding grid keeps equilibrium problem as a Nash game, Nash equilibrium game. Is it clear? Very good. So we discussed that it's profit, utility, and congestion rent. And here we explored the objective function is indeed congestion rent. Okay. The last important things, and then we will have a Kahoot quiz. I picked the generators problem, but you can have the same analysis for all other players. The question is that can we prove the cost recovery of producers? And what cost recovery means? Also, you can cost recovery is also referred to as individual rationality. If you read game theoretic text, usually it's called individual rationality rather than cost recovery. Cost recovery says that market players, everyone, like generators here, they will never achieve negative profit. They always achieve a non-negative profit, a profit which is zero or positive, but not negative. Meaning that the market payments for this generator, the market payment is sufficient to cover the cost. The cost is CG. If we can prove it by design, not numerically, by design, then it's considered as a desirable economic market property. So what I'm saying is, when I say market property, okay, you may one day work for a market operator. There are many papers in the literature that say, let's design a market. Oh, of course, you can design a market, but there are some good properties that we are looking for. So you cannot design any random market, say that, okay, we like to have this market. So one of the important properties that we like to have in the market, one of them is cost recovery. It means that if for generators, for demands, for storage, for everyone, if they participate in the market, we should guarantee them that you will not lose. I'm not saying you will earn or not, how much you will earn. I'm not saying that. It's up to you. It depends on your strategy. But what I guarantee is that you will not be bankrupt. Your profit will not be negative. Is it clear? So maybe from optimization problem, we couldn't see it clearly. But by seeing this equilibrium problem, and we know that equilibrium problem is now equivalent to optimization problem of maximizing social welfare, is it trivial for you that the profit will never be negative? Is there any way that the profit of generator could be negative? Yes? No, let's say price is positive. But even if price is negative, even if the price is negative, is it there any chance that you earn negative profit?
No, because just maximize it by setting PG to 0.
Yes. Always you can set PG to be equal to 0. So what PG to be, it's your decision. So you set PG equal to 0, so then the minimum earning that you can get is 0. Yes?
Does that take into account that you have expenses whether you produce or not?
Yeah. You have expenses what?
Whether you produce or not. Like,
No, PG, your decision is how much you produce, and it could be between 0 to capacity, for example, 100. You have that option to choose. You see what I'm saying?
yeah, but I mean, you have to pay rent or whatever. Right?
Yeah, we are only talking about CG, the operational cost. Cost recovery of operational cost. Are we talking about investment cost? No. So here I'm only talking about you will be able to recover cost CG, not any constraint that we don't see it here. Good. A question. If instead of 0, the lower bound was P min, for example, 10 megawatt, could I guarantee anymore there will be a cost recovery? Not anymore. Not anymore. Okay. So that's why also in your assignment, please assume P min for all generators is 0. Is 0. Good. Yay. One more question before Kahoot. So here we have 4 type of players: generators, demands, transmission owner, and price setter. If I add storage, and task 2 after assignment 1, you are adding storage, right? Where will, the storage, is it gonna be, where we can add storage here? Or any other device, electrolyzer, heat pump, whatever. They are not generator or demand or owner of transmission grid or price setter. If we add a new technology, new asset, what should we do?
Formulate a new optimization.
Exactly, a new box. A new box. And still you will see that if you add storage, electrolyzer, whatever you like, you will still see that equilibrium and optimization problems are equivalent. So in your case, that now you are adding storage in your assignment, let's say that now we are adding a new box here for the storage, for the battery. So we like to maximize something subject to something. Can you tell me that what the objective function for storage will be? The constraints are clear, right? There are charging constraint, discharging constraint, the energy stored in the battery reservoir. So the same constraints that you also added to the market clearing optimization problem. But what is the objective function? That's my question.
You need to maximize both generation and demand.
Yes.
Charging and discharge.
Yes.
So we want profit, the profit for.
Yeah. Yes. Remember, grid owner is a spatial arbitrator. Who does arbitrage between nodes? Battery is the same, buying and selling, not between different nodes, between different hours. So the objective function will be still arbitrage, but temporal arbitrage profit. So it will be P charging in lambda T, that's your cost, you charge, minus P discharge times lambda T prime, for example. So now I would say opposite. So now this is a cost. So what you earn is P discharge times the price in that hour minus P charge in times the price in the hour that you are doing discharge. Is it clear? So you can write a similar optimization problem for storage and add it to your equilibrium, and you will see that it's the same. Paul said, do you have any example where the market clearing price becomes a generalized Nash game? Can you give me an example? The very clear example is that if you realize you can, for example, as a generator, withhold, if you, for example, realize that PG, your production, could change lambda. For example, you say that PG, if you know that you have market power, you say that PG, my production, is a function of price, alpha times lambda plus beta. And you are trying to learn what alpha and beta is. You are trying to impact price. Then it will become a generalized Nash game because lambda appears also in your constraints. So market power is a clear example that may kill NE and make equilibrium problem GNE. So Paul, I hope it's clear to you online. Good. I told you 2 forms, optimization and equilibrium. There's third form, which is MCP. You derive KKTs either of optimization or equilibrium. Then it's a system of equations. There is no objective function. It's MCP, mixed complementary program. Also using path solver, or maybe there are also other solvers. You can solve this directly. Are you going to do that? It's not computational, it's not logical, I would say. But there is also the third form that you can solve that and clear the market. I talked for 2 hours to you just to reach to this conclusion. All three forms of market clearing problem means optimization, equilibrium, and MCP, mixed complementary program, are equivalent. So when you solve social welfare maximization optimization problem, implicitly you are also solving equilibrium problem. Implicitly you are also solving MCP. That's good. Ready? Okay, I have to open first my Kahoot. And this time you only have 10 quiz. So number of quizzes is 10. It's coming. Yeah, please join. So there are only 10 quizzes this time. $92 signed up so far. $95. $96, $97. Okay. Is there everyone is still trying to join? Okay, let's get started. Yeah, we're quick. We just discussed that. Okay, apparently 30 seconds were too much for this question, too long. Yeah, we have to wait. Yay! Yes, you can solve the market clearing problem as an optimization, as an equilibrium, as an MCP. That's the conclusion we draw. So the GOAT leading. Quiz number 2. Who does enforce power balance equality in the equilibrium model? Yes, price setter. Price setter is the one that enforces the power balance equality for each node. Network owner, just we saw, it only enforces the network constraints. Here we are talking about power balance constraints, which is the optimization problem of the price setter. Albert now is leading. Quiz number 3. Oops, it's... What is the objective function of the grid owner? It's the... I'm sorry, there is something wrong. It's only blue one. Blue is correct. Congestion rate maximization. So if everyone put the power balance, it's okay. But for Kahoot, it's correct, but it's wrong. So the correct answer is congestion rate maximization. That's what grid owner maximizes. So who picked the grid? You are lucky in terms of Kahoot. But the answer is wrong. Still Albert leading. Quiz 4. That's a tricky question. Which one is a Nash equilibrium, NE? Blue one is Nash game. I will explain this afterwards. But the blue one is the one that represents a Nash equilibrium. Well, ST7. Quiz number 5. Which one now is GNE? The same choices. Good. Yellow one is the GNE. Okay, now let me explain you. The red one, we have two optimization problems. The first one only and only depends on x, both objective function and constraints. The second optimization problem is only and only depending on y. So it's two separate optimization problems. There's no linkage between two optimization problems. It's not equilibrium problem at all. Two independent optimization problems. Blue one, they are independent because optimization in the left, it optimizes x, but objective function also depends on y. And y is the variable of the second optimization problem. And also x is impacting the objective function of the one in the right. So the blue one is Nash equilibrium because two optimization problems, they are impacting each other's objective function, but not constraints. It's like our equilibrium problem that we discussed. The yellow one is GNE because two optimization problems, they are interconnected through objective function and also constraints. It's a GNE. And the last one is not equilibrium at all. It's a single optimization problem. It's a co-optimization problem. Right? So I hope now it's clear to you. Okay, let's see now who's leading. Still CD7. Now quiz number 6. I just said that. Yes, I just discussed the competitive equilibrium model is a Nash equilibrium. Different agents, they only impact each other's objective function, not constraints. So the competitive equilibrium problem we discussed, it's a Nash game. GNE is wrong. It says includes multiple independent optimizations. So yellow is also wrong. And the only correct answer is red. So let's see who is leading now. It's still CD7. Quiz number 7. It's a definition of Nash equilibrium point. Yeah, blue one. Under Nash equilibrium point, no one will be able to unilaterally change its decision to increase its profit. So that's the classic definition of Nash equilibrium point. That's what John Nash proved. So let's see who is leading. Still CD7. Quiz number 8. Well, the majority found the right answer. I'm very happy that teaching KKTs paid off. Yes, we drive KKTs. If they are identical, then the corresponding problems are equivalent. Very good. Let's see who is leading. Still CD7. Quiz number 9. What is cost recovery? It's all. Yes, cost recovery is a desirable market property. We want it. It implies that the profit of every market player is non-negative. It's correct. It can be mathematically proven by the equilibrium model. Yes, we did that. We did that putting production equal to 0. It's a solution. It's a feasible point. So all is the correct answer. Well, now Schwartz is leading. And be ready to the last question. Last quiz. That's a tricky one. Green is correct. Let's figure it out. We have 3 producers. Each of them try to maximize their own profit. So we have 3 optimization there. 4 demands. Each of them, they are trying to maximize their own utility. So we have 4 optimization there. So far 7. We have 5 lines. It means that there is a grid owner. And we have only 1 optimization problem for the grid owner maximizing congestion rent. So that's the 8th one. And we have a price setter. So 9. So congrats to those who picked 12. That's really good job. So number 3, the gold. Second, L. 1, Schwartz. So, who is Schwartz? There. Congratulations. What's your name? Catherine. Are you alone or you are in the group? Okay, Catherine won today the quiz, the code quiz. Congratulations. And thank you, everyone. See you next time.